So welcome you all in the 23rd lecture of embedded system. So in the last lecture we have talked about the mainly the priority inversion protocol and priority ceiling protocol. So priority inversion protocol was proposed to invert the priority, right? Why because automatically the lower priority task was becoming the higher priority, and because of that, and the waiting time for a particular task was getting longer and longer, right? So to reduce the waiting time of a high priority task which needs a critical section, so we were trying to overcome that problem using the priority inversion protocol. But because of nesting of critical sections, in which one critical section we are accessing, or the processor is accessing another critical section, so that was leading to some deadlock problem, right? So that deadlock problem was resolved by using priority ceiling protocol, right? So this was all about scheduling, which we have studied in a real time system, that how scheduler schedules different tasks, right? So the scheduler was we have proposed that was actually uniprocessor, so that means there was only one processor at a time, and we have not considered initially the any resource constrained environment, and then later on we have taken that resource constrained environment also, right? So in real time system can also do some voltage variation, okay? So voltage, for example, operating system can assign, so let's say that there are T1, T2 and T3, okay? So we have three tasks, right? And we have the information of their arrival time, their deadlines, right? So what we could do, we can, right now we are actually running all the tasks at a fixed voltage, right? We are running at a fixed voltage. For meeting the criteria that the deadline of each task should be met, right? That is a real time system. So the deadline should not be missed in a real time system. So now if the task is, some of the tasks are scheduled much faster, so what could we do? We can optimize the power required, right? So actually what we could do, we can, if there is a possible availability of free time, so we could vary the voltages of different tasks, right? For example, T1 can run on a different voltage, okay? So let's say that initially all three were running at a 5 volt, right? But we could vary, we can vary the voltage levels of each task. For example, T1 can run at a 4 volt, T2 can run at maybe 3 volt, let's say, right? And so on. So the idea here is this kind of scheduling in voltage is called as voltage scheduling. Voltage scheduling. And this we have given in short introduction about the voltage scheduling in the scheduling class. Now we will see actually what is voltage scheduling in detail, okay? So then the idea comes, why there is a need to go for the voltage scheduling, right? So first the curiosity will come to your mind, that why do we want to change the voltages of each task, right? So to get that motivation, we will see some couple of slides. So we see that there is a power density problem. So what is that power density problem? So what we are doing actually in basically when we go from initial processor to a Pentium 3 processor, the power is, the power dissipation is increasing and continuously, right? So we see that in a Pentium Pro processor, it is, we are actually packing more and more, contains in a small chip, right? So the dimension of chip is getting reduced over the time, and the power dissipation is getting increased, right? So we have to dissipate some power, because we have to dissipate some power, and the size of the chip is getting reduced. So already we have reached actually to the hot plate, so that means you can cook anything, right? So that means power it is dissipating, and we are going towards the higher end processors, where the power dissipation could reach the power equivalent to nuclear reactor, right? So uh, there is something called area and power envelope, right? So our area is restricted, right? So our silicon area is restricted, where we have to place all the integrated components such as transistors, right? So we have to accommodate a lot of transistors and other electrical components. So right now, let's say that these are the number of processor on number of the processor cores. So, and this is x-axis denotes the your cache size. So the idea here is that most of the time power is consumed in memory access, right? So we want to perform any operation, we have to take the data from the memory. So more than a processing, this communication or accessing the data from the memory takes more time than the actual computation. So what we could do, we can actually to fit a lot of cores to reduce the time of execution, we can increase the cache size. Okay, so cache size means it is SRAM basically used for cache size. So if cache size is more, then the operation could be much faster. Okay, so but there is a limitation, so due to the area, right? So we have the limited area, we cannot increase that area, and we could increase the number of cores, but it is not always the case, right? Because when you see this dark line, when you see this curve, what is this curve actually? This curve says that we could actually reach 10 number of cores at max, and your cache size can be limited around 55 MBs, right? Why is it so? So that means you have a silicon area in a chip, but you cannot ignite all the silicon areas, right? So we are not actually triggering all the silicon area in your chip, and that is called as dark silicon, right? So most of the silicon area is not activated. So so many of the cores are unusable. So if you keep even more and more number of processor cores, that will remain unusable, because we are restricted by the power and area, right? So what could be the solution actually? So we cannot use them all, we cannot use all the processor at their highest speed, right? So for example, if you let's say if you take 128 number of cores, so if you map it, your cache size could not be that big, you cannot take that much cache size, right? And if you increase the cache size, you have to reduce the number of cores, right? So your actual execution is limited by this black curve, right? But our aim is to reach up to max, right? So what could be, I can take maximum cache size and maximum number of cores. Okay, so what could be the basic solution? So that basic solution is nothing but the voltage change, right? So if you can somehow, if you can change apply different voltages to different tasks or to different cores, you can actually cross the dark silicon curve, right? So for example, your area is limited by 310 millimeter square, and your power is also limited, right? So this was the dark silicon where area and power is limited, right? We cannot exceed that, area and power curve. But if when you see that, if you use the different clock frequencies at different voltages, right? So we could able to cross that black curve, right? So so this shows that we could able to reach to the maximum execution time, but it is not possible in a real time. So ideally optimized, if you count it, we could actually go to somewhere around 44 cores by keeping these requirements of area and power, right? So what could be the voltage change? How can a scheduler do the voltage change for a different task, right? So this we have seen that there are basically three types of scheduling, basically two types of scheduling, but that is categorized into two categories. So we will see what is that two category. One is static voltage scheduling, and another was your dynamic voltage scheduling, right? So what is actually, and that this dynamic is also further divided into two category, so that we will see what is those two category. So what is actually static voltage scheduling? So in a static voltage scheduling, I'll write it down like SS. So what is this actually? In this voltage scheduling, we know the arrival time of all tasks. So we know that arrival time of all tasks. Okay, what else we know? We know about the deadline also, right? We know the deadline of all tasks. And third thing, we know that what is the worst case execution time, okay, and or we call it as worst case execution cycle of all tasks, that is also known. So if all these three things are known, we could actually assign the task, or we can schedule all the tasks at the offline level, right? So there is no need to go for online level, right? So what is actually that we will see. So let's say that your this first task came T1. We have, let's say that we have two tasks, T1 and T2. So this is your T1 and this is your T2. So T1 has arrived first at this position, so there was no other task, so T1 has been scheduled, right? And this is your deadline of your T1 task, and T2 came somewhere around here, right? So T1 is already, so this is your T2 task, right? So you, at this time when your T2 is arriving, T1 was already executing, right? So T2 could execute when the T1 is ended, right? So T2 is able to start here, and it will run, it will finish it, right? And this will be your deadline of your T2, right? So what is this worst case execution time? So this is your worst case execution time, and this is your deadline. Okay, this is your arrival time, and this is your release time. So when the task is released for execution, right? So we know already the information. So what we could do, so we know that when the T2 is coming, right? So what I can do, I can do two possible things. One thing I can do that I will run a T1 at a maximum voltage, okay, so that this T1 can be finished earlier and I could start at this point, right? So if T1 is finished earlier, I can start T2, because we know the arrival time of all the task, right? So this is your, let's say this is your T1, and I run this T1 at a higher voltage, so it is finished earlier, right? So then I could then if I draw the T2 also, so let's say that T2 has arrived at this position, right? So if I execute in the as a previous voltage, so this was actually the your T2 and this is your deadline, right? So when I execute T1 at a higher voltage, I can get this free time. Okay, this is your free time. Okay, so what I can do, what I can do basically, I could shift this T2 here. Okay, so what I can do, let me draw with a different color. So what I will do, this T2 I will run at a lower voltage from here, and I know the deadline also, right? So I could actually run this T2 at a lower voltage, right? So let's say that another task also came, so at that position I could increase the voltage level of T2 and I can finish all the tasks, right? Because we know the arrival time of each task, deadline of each task, and worst case execution of each task. So right now, what is dynamic voltage scheduling? In dynamic voltage scheduling, so in dynamic voltage scheduling, okay, so one more thing I should say before dynamic scheduling, that let me write that first. Okay, so one possibility was actually that we have seen that in the previous slide. So this is known as SS means you have the static scheduling, okay, and static voltage. So what is the meaning of 2S? If you count down the 2S means your static scheduling and static voltage. So this was the case we have seen in this particular task, right? Now what we did in the next case, that we have changed the voltage of T1 at a higher voltage. So this was somewhere here. So now I have run T1 at this position, so it was finished earlier, right? So when this was finished earlier, what I did actually in this case, because I know the arrival time of the next task or other task, so I was able to increase the voltage of T1. So in this case my scheduling is static, right? Scheduling I am doing at offline, so my scheduling is static, but voltage is dynamic, right? So this is called as, I am denoting it as SD. Now in the next case, there is a dynamic scheduling. So what is that dynamic scheduling? What is the dynamic about it? So the dynamic scheduling, that we know that we don't know the arrival time, first of all. Okay, we don't know the arrival time. So what we know? So we don't know the arrival time, right? So in this case we have to take the decision dynamically completely, right? Because we don't know the arrival time, but we know the deadline, right? We know the worst case execution time and deadline that we know, right? We have this information. Now how can I assign a task in a dynamic scheduling? So let's say that this is your task T1, this is your task T1, and this is your deadline of T1. Now at this position, let's say your T2 comes at this position. If I write it down, so this is your arrival time of your T2, and scheduler doesn't know this thing, right? So dynamically it has to take decision, right, when I want to schedule it. But in that uh, static SS case, static scheduling, static voltage case, I was assigning the task statically and the voltage also fixed. But in SD case, I'm assigning it offline, but dynamically I could able to change the voltage. But here we don't know the arrival time, so T1 was executing, T2 came suddenly. Now what this has to do, right? So T2 cannot be executed until this T1 is finished. So T1 is finished here, so it will execute, let's say, till here, and this is your deadline of your T2, right? So the new task, let's say that this new task T2 came. So what it can do, it can preempt. So if the priority of T2 is higher than T1, it can preempt the task, because we don't know that it's a dynamic scheduling. So if any more priority task came, obviously it can prevent that previous task and it can start right, or it can wait for the completion of the previous task. Is it clear? Now who will decide that, who will manage that, it is a preemptive task or it has to wait? So operating system has to take care of that, right? So operating system will take care of that. Now what are the different possibilities in a dynamic case? So in dynamic case, what I can do, I can assign, here I don't know, actually at this position I don't know there was another task. Now at this position I got to know that there was another task which has arrived. Now what I can do, I can actually I can actually see that what is the deadline of next task. Okay, so if the deadline can be met, I can check, right, using this worst case execution time. I can easily check that will I able to will I able to meet the deadline of the next task, right? So I have two possibilities. I could able to run at particular voltage, or I can decrease the voltage and finish it here, right? So still, if this task will start from here, still I am able to meet the deadline, isn't it? So these all things should be optimized, right? So we have to optimize that what is the worst case execution time. So using this worst case execution time, I can take any action, and that action will be completely dynamic, right? So T2 can also further decide based on another arrival of another task. So T2 can also govern its own voltage, so it could run at a lower voltage because it has so much of time to complete before the deadline, right? So it could reduce the voltage if any other task also came at that same time. It could increase that it could increase the level of its voltage and finish earlier, right? So that the deadline of other tasks should be met. So what is the important thing here? The important thing is to meet the deadline. Met the deadline. So if I summarize this scheduling, so these schedulings are basically, so if I write down here, this is SS, this is SS is we will leave because it's completely statically scheduled and static voltage, so we can leave. But what is the basically difference between SD and DD? So in SD, your CPU time allocation, if I write down CPU time allocation, so I could assign any time the task because I know the arrival time. So this is done offline, and in this completely online, right? Now next is start time assignment. So when the task should assign, depending on the preemption is there or not, or if I don't allow it, will it able to complete its deadline. So that is start time assignment. So that is done on time. Oh, sorry. So that is done online because that decision I can take. So this is the dynamic in that, right? So I can take the decision, okay, deadline is so much longer, so I could reduce the voltage, right? So that is done only online, right? And here this is also done online. End time assignment, that I can do easily offline because I know the deadline, right? That can be, I know the deadlines, I can fix it at the offline level that okay, so you have to finish the task before the deadline. So this assignment can be done offline. Here that is also done online, right? Okay, so by doing this voltage scheduling, we could able to cross that dark silicon curve, right? So now why is this useful? Actually, if you see why this voltage scheduling is useful, so voltage scheduling is very important to optimize the power consumption of embedded system, right? So if you see one study, so so there you can actually, so there was study done actually for different tasks. So if I write down the numbers, so energy, so there were 7 tasks which were given to different scheduling. So if I write down the energy numbers, okay, so that was actually reducing. So in a static case, it is somewhere around 16-15 joule. So it is reduced in 700 around joule. And dynamic scheduling, the energy consumption is higher, but we cannot compare these two because this is completely dynamic. We don't know any information about the task, right? But from SS to, so this is your SS, SD and DD, right? So from SS to SD, we were able to reduce the energy. Okay, so wherever it is possible, we can go from SS to SD, right? This is not possible here because of uncertainty of